Time can be run backward, not in a story, not as a manner of speaking, but for real, on a machine, on a laboratory bench, in a chamber chilled almost to absolute zero. It has already been done. A small piece of the world was made to run in reverse, its disorder gathering back into order, the forward march of time simply undone for a moment. And that is only the first of 3 strange things these machines can do to time, because they can also erase the difference between before and after, and they can build a working clock out of nothing but connection. Each one, on its own, is unsettling. Together, they point toward a conclusion about time that a growing number of physicists find genuinely frightening. By the end of tonight, you will know exactly what quantum computers are revealing about time and exactly why it is so terrifying. What is left of the word now, when a machine can take time apart piece by piece? Get cozy and settle in. Subscribe if you have not already, and stay with us, because the path to that answer runs through a reversed moment, a dissolved order, and 2 particles of light that hold an entire universe between them. Let's dive in. Part 1. The machine that ran time backward. Somewhere in a laboratory, inside a metal cylinder chilled to within a whisper of absolute zero, a small quantum system was about to do something the rest of the universe never does. It was going to move backward in time. Not in a movie, not in a metaphor, not in some loose figure of speech about nostalgia or memory, but in the literal, measurable sense that a physicist would recognize. A state that had spread out and grown disordered was about to gather itself back together and return to exactly where it had been a moment before, as if the intervening moment had been quietly deleted. And the thing making this happen was not a wormhole or an exotic new force, it was a computer. In the year 2019, a team of physicists spread across 3 institutions, the Moscow Institute of Physics and Technology, the Swiss university known as ETH Zurich, and Argonne National Laboratory near Chicago, published a short paper with a title that reads almost like a dare. They called it Arrow of Time and its Reversal on the IBM Quantum Computer. The words are worth slowing down on, because each one is doing real work. The arrow of time is the name physicists give to the single most reliable fact about the universe, the fact that things move from order toward disorder, from past toward future, and never the other way. And these researchers were claiming in plain language that they had reversed it. Not metaphorically. On a machine. One you could rent time on over the internet. Here is what they actually did, and it is worth understanding precisely, because the precision is where the strangeness lives. They took one of IBM's publicly available quantum processors, the kind any researcher anywhere in the world could log into and use. They prepared a simple quantum state, something clean and localized, the quantum version of a tidy little ripple sitting in still water. Then they let it evolve. Left to its own devices, that neat ripple did what everything in nature does. It spread out, it dispersed, it lost its shape and slid toward disorder, the way a drop of ink released into a glass of water blooms outward until the whole glass is faintly, uniformly grey. This is the arrow of time in its most ordinary costume. Order becomes disorder, the drop becomes the haze, and it happens on its own without anyone pushing. Then the researchers did the thing that should be impossible. They ran a carefully designed sequence of operations on the processor, a short program built around a specific mathematical move, the move that reverses the direction of quantum evolution. And on their screens, the impossible unfolded as ordinary data. The dispersed, disordered state pulled itself back together. The haze became the drop again. The ripple reassembled. The system returned to the exact configuration it had occupied before it started to spread, as though someone had taken the film of a shattering and run it backward until the pieces leaped up and formed a whole. The lead researcher, a physicist named Gordy Lesovic, described what they had made in a single sentence that I want you to hold on to for the next 2 hours. They had artificially created a state, he said, that evolves in the direction opposite to the thermodynamic arrow of time. Now, you might reasonably think this is a trick, a bit of clever bookkeeping dressed up in dramatic language, and in a sense you would be right to be suspicious, because the truth here is stranger than a trick. What the experiment revealed is not that the arrow of time is easy to break. It is that the arrow of time was never a law in the first place. It was only ever a matter of odds. Overwhelming, astronomical, universe-sized odds, but odds all the same. And a quantum computer, it turns out, is a place where you can pay those odds by hand. You can put up the impossible price that nature never pays and buy yourself a moment running backward. To feel why that is so unsettling, you have to understand what the arrow of time actually is and what it is not. Every one of us lives inside that arrow so completely that we almost never notice it. You remember yesterday but not tomorrow. You watch a cup fall from a table and shatter on the floor, and you know, without being told, that you will never see the reverse. The shards gathering themselves up off the tiles, leaping back onto the table, reassembling into an unbroken cup that was never dropped. The forward direction of time is the most obvious thing in the world. It is so obvious that for most of human history nobody even thought it needed explaining. Of course, time moves forward. What else would it do? But here is the quiet scandal that sits underneath physics, the thing that most people are never told. When you look at the fundamental laws that govern how the universe changes, the equations of motion that physicists have spent 4 centuries refining, not one of them contains that arrow. Newton's laws of motion run equally well forward and backward. Play a film of 2 billiard balls colliding, then play it in reverse, and both versions obey Newton perfectly. Nothing in the physics tells you which is which. The same is true of the equations governing electricity and magnetism. The same is true of the equation at the heart of quantum mechanics, and the same is even true of Einstein's equations for gravity and the shape of space and time. Flip the direction of time in any of them, and you get another perfectly lawful history. The laws do not care which way time points. The arrow is simply not written into them. So where does it come from? Why, if the laws are indifferent to direction, does the cup always shatter and never reassemble? Why do you age in one direction only? This question is one of the deepest in all of physics, and the answer that emerged in the 19th century is subtle, and, once you really absorb it, a little vertiginous. The arrow does not come from the laws, it comes from counting. It comes from the fact that there are vastly more ways for things to be disordered than ordered, so that a system left alone will almost certainly drift toward disorder simply because disorder is where nearly all the possibilities live. The cup shatters and never reassembles, not because a law forbids the reverse, but because the reverse, while perfectly legal, is so improbable that you would wait many times the age of the universe to see it happen by chance. That word, improbable, is the hinge on which this entire story turns. Improbable is not impossible. Improbable means there is a price, and the price is astronomical, and nature almost never pays it. But a quantum computer is a machine built precisely for controlling small quantum systems with exquisite care. And in a small enough, controlled enough system, you can do by deliberate design what nature will not do by chance. You can arrange the exact conditions, apply the exact operation, and force the disordered state to retrace its steps. You're not breaking the second law of thermodynamics. You're paying the odds by hand, putting up, in the form of precise control and careful engineering, the impossible improbability that the universe never spontaneously spends. And when you pay it, time runs backward in your little corner of the machine. The researchers even measured how hard the price is to pay, and this is the detail that turns the experiment from a curiosity into a genuine window. On a version of the experiment using 2 quantum bits, 2 qubits, the reversal succeeded about 85% of the time. But when they scaled it up to 3 qubits, the success rate fell. More qubits meant more ways for the delicate operation to go slightly wrong, more places for the reversal to fail, and that falling success rate is not a flaw in the experiment. It is the second law of thermodynamics appearing right there in the data, in miniature. It is a direct measurement of why the universe at large never runs backward, because the bigger the system, the more astronomically improbable the reversal becomes, until for anything the size of a coffee cup the price is so far beyond any machine that it might as well be infinite. So we begin with a machine that did the impossible by paying for it. And already, standing at the doorway of this story, you should feel the first floorboard shift under your foot. If the arrow of time is not a law but a matter of odds, and if a machine can beat those odds in a small enough system, then a question opens that we're going to spend the rest of this journey following down into the dark. What else about time that we take for bedrock, the order of before and after, the very existence of a passing now, turns out to be something a machine can take apart. The reversal was only the first thing these machines revealed. It is not the strangest, not by a long way. Part 2. An arrow made of odds. Let us stay with that arrow a little longer, because before we can appreciate what the machines are dismantling, we have to feel the full weight of the thing we always assumed was solid. The forward flow of time is not one fact, but a bundle of them, and they are so tightly wound together in ordinary life that we never think to separate them. There is the fact that we remember the past and not the future. There is the fact that causes come before effects. There is the fact that broken things stay broken, that heat flows from hot to cold and never back, that a drop of ink spreads through water and never gathers itself into a drop again. All of these feel like the same fact wearing different clothes, and all of them, physicists eventually realize, trace back to a single source, and that source is not a law of nature but a kind of cosmic bookkeeping. The person who first saw this clearly was an Austrian physicist named Ludwig Boltzmann, working in the 1870s, and what he understood changed the meaning of time itself. Boltzmann was thinking about heat and gases, about why a warm room and a cold room, open to each other, always settle into one lukewarm room and never spontaneously separate back into warm and cold. He realized that the answer had nothing to do with any force pushing the temperatures to even out. It had to do with counting the arrangements. There are countless ways for the air molecules to be all mixed up at one uniform temperature, and only a vanishingly tiny number of ways for them to be neatly sorted into hot on one side and cold on the other. So when you let the system do whatever it likes, it wanders, essentially at random, and because the mixed-up arrangements so wildly outnumber the sorted ones, it almost always ends up mixed. Not because it must. Because the odds are overwhelming. Boltzmann captured this in an equation so central that it is carved on his gravestone, a short formula relating a quantity called entropy to the number of microscopic arrangements that look the same from the outside. Entropy is, roughly, a measure of how many ways a thing can be arranged while still looking the way it looks. A shattered cup has enormously high entropy, because there are countless ways for those shards to be scattered that all count as broken. A whole cup has low entropy, because there are relatively few ways to arrange the atoms into a perfect unbroken vessel. And the second law of thermodynamics, the law that gives time its arrow, says simply that entropy tends to increase, that systems drift from the few, ordered arrangements toward the many, disordered ones, for the same reason that a shuffled deck almost never comes out sorted. The arrow of time is the arrow of the odds, but here is where it gets subtle, and where a contemporary of Boltzmann's put his finger on exactly the sore spot that the quantum computer would press on a century and a half later. A physicist named Joseph Loschmidt raised an objection that has haunted the subject ever since. If the underlying laws of motion are perfectly reversible, Loschmidt pointed out, and they are, then for every process that increases entropy, there is a mirror image process that decreases it, and the mirror image process is exactly as lawful. Imagine you could reach into a system and reverse the velocity of every single particle, flip each one to move in precisely the opposite direction, at precisely the same speed. If you did, the system would obediently retrace its entire history backward. The mixed air would unmix, the shattered cup would leap back together, entropy would run downhill. And nothing in the laws of physics would be violated because the laws work the same in both directions. Loschmidt was right. That is the uncomfortable truth at the base of the whole edifice. The reason we never see entropy decrease is not that it is forbidden. It is that reversing the velocity of every particle in even a droplet of water is so far beyond any conceivable technology that it functions, for all practical purposes, as an impossibility. There are more molecules in a single raindrop than there are stars in the observable universe, and to reverse the arrow you would have to catch every one of them and flip it, perfectly, simultaneously. Loschmidt's reversal was a thought experiment precisely because no one could ever do it. It lived in the world of pure principle, a loophole in the arrow of time that was real but forever locked away behind an impossible door. And now you can perhaps feel the ground shifting again, because you already know what happened to that impossible door. A quantum computer is a machine for controlling a small number of quantum systems with a precision that borders on the absurd. It cannot reverse a raindrop, but it can reverse a 2-qubit or 3-qubit state, because with only 2 or 3 quantum bits to manage, the impossible price of flipping everything at once comes down from cosmic to merely difficult. That is precisely what the 2019 experiment was. It was Loschmidt's thought experiment, made real in the one arena small enough and controlled enough that the reversal could actually be performed. The team designed the operation that plays the role of reversing every velocity, a mathematical move called complex conjugation, the exact operation that runs quantum evolution backward, and applied it, and watched the state retrace its steps. There is an older cousin of this trick, and it is worth knowing about because it shows that laboratory time reversal is not brand new, only its extension to a general-purpose computer is. Back in 1950, a physicist named Erwin Hahn discovered something called the spin echo. If you take a collection of atomic nuclei, each one spinning like a tiny top, and you nudge them so they all start spinning in step, they will gradually fall out of step with one another, fanning out into apparent disorder, their signal fading away as if it were lost for good. But Hahn found that if you apply a precise pulse that flips them all at the right moment, the nuclei that had fanned out will reconverge, marching back into step, and the lost signal will reappear, a faint pulse pulled back out of the noise. It is a partial reversal of a small piece of the arrow of time, achieved with radio pulses, and it has been quietly used in laboratories and hospitals for decades. The quantum computer simply takes this idea and makes it programmable, general, precise, a reversal you can dial up on demand for whatever state you like. There is an even deeper twist to Loschmidt's objection, one raised a few years later by a mathematician named Ernst Zermelo, and it presses the sore spot harder still. Zermelo pointed out that any closed system, left alone long enough, must eventually return arbitrarily close to any state it was ever in, a result that follows from the mathematics of how such systems wander through their possibilities. Given enough time, the shattered cup really would reassemble, the mixed air really would unmix entirely on its own, no machine required. The catch is the phrase, enough time, because the waiting time for such a spontaneous return, for anything larger than a handful of particles, dwarfs the age of the universe so completely that the numbers lose all meaning. But the principle stands, and it sharpens the knife. Boltzmann's own mathematics, taken by itself, is perfectly even-handed about direction. It predicts a high-entropy past exactly as readily as a high-entropy future. The equations do not know which way is forward. They never did. The forwardness had to be added by hand, in the form of an assumption about how the universe began, that it started, for reasons no one can fully explain, in a state of extraordinarily low entropy, extraordinary order, and has been unspooling from that ordered beginning ever since. The arrow of time, in the end, may be less a feature of the laws than a memory of the universe's first morning. Once you understand that the arrow of time is made of odds, and that odds can in principle be beaten, a strange new feeling settles in. The forward march of time, the thing that separates the living from the dead and the done from the still possible, stops looking like an iron law of the cosmos and starts looking like a habit, an overwhelmingly reliable habit, a habit the universe keeps every single time at the scale of cups and people and stars, but a habit nonetheless, not a commandment. And habits, unlike commandments, can be broken by someone willing to pay the price. In a cold machine on a laboratory bench, someone paid it. But if the arrow of time is only a matter of odds, you might still hope that somewhere deeper down, in the fundamental laws themselves, there is at least a whisper of true direction, some tiny built-in preference for forward over backward, written into the fabric of the particles that the counting merely amplifies. For a long time, physicists hoped exactly that. They went looking for it, and what they found, when they finally found something, was so faint and so strange that it deepened the mystery rather than resolving it. To see it, we have to leave the world of cups and raindrops and go all the way down to the smallest things that exist, where the laws are written in their purest form. That is where we're going next. Part 3. The One Place. The law bends. If the everyday arrow of time is only a matter of odds, then the natural next question is whether the fundamental laws contain any genuine direction at all, any real, built-in difference between forward and backward, however small. For a long time this looked like a lost cause. Every fundamental interaction physicists studied ran the same in both directions. Reverse the film and the physics held. It seemed the microscopic world was perfectly indifferent to the direction of time, and the arrow was entirely a creature of statistics, of counting, of the odds we have just been exploring. And then, in a corner of particle physics that almost no one outside the field ever hears about, a crack appeared. The story begins in 1964, with an experiment that won its authors the Nobel Prize and unsettled the foundations of physics. Two researchers, James Cronin and Val Fitch, were studying a strange short-lived particle called the neutral kaon. What they found was that a certain process involving these particles happened at a very slightly different rate than its mirror image, that nature at this tiny scale, was not perfectly symmetric between a process and its reflection. The specific symmetry they found broken is known by the shorthand CP, and the discovery that CP could be violated sent a shock through the field. It meant the universe was not perfectly even-handed. Somewhere in the hidden machinery, there was a faint thumb on the scale, a preference, a difference between one way and its mirror. Now, there is a profound theorem in physics, one of the most solid results we have, called the CPT theorem. It says, in essence, that if you take any process and simultaneously reflect it in a mirror, swap every particle for its antiparticle, and reverse the direction of time, the result must be a perfectly lawful process. That this triple combination is an unbreakable symmetry of nature. The theorem is woven so deeply into the structure of modern physics that almost no one expects it to fail. And it has a startling consequence. If that triple symmetry always holds, and if the first two pieces of it, the mirror reflection and the particle-antiparticle swap, can be violated, as Cronin and Fitch had shown, then the third piece must be violated too, in a way that exactly compensates. In other words, CP violation implies time reversal violation. It implies that somewhere in nature there is a process that runs at a different rate forward than backward, a genuine law-like arrow buried in the particles themselves. For nearly 50 years that arrow was only inferred. Physicists were confident it had to be there, because the CPT theorem demanded it, but no one had ever caught time reversal violation directly, in the act, on its own terms. Watching it directly is fiendishly hard, because it means comparing the rate of a process against the rate of that very same process run backward, and you cannot simply run a particle interaction backward the way you rewind a tape. You need a clever experimental design that gives you access to both directions of the same transition, and in 2012, an experiment finally managed it. The experiment was called Babar, running at a laboratory in California, and it studied not kaons but a heavier cousin, particles called B-mesons, produced in enormous numbers by smashing beams together. What Babar did was watch these B-mesons transform from one quantum state into another, and compare the rate of that transformation against the rate of the reverse transformation, using entangled pairs of particles to get at both directions cleanly. The comparison revealed a clear difference. The forward process and the backward process happened at measurably different rates. It was the first direct observation of time reversal violation in the history of physics, the first time anyone had watched, head-on, a process in nature that genuinely distinguishes past from future. And the statistical strength of the result was overwhelming. Physicists measure their confidence in units called sigma, where 5 sigma is the threshold for claiming a discovery, corresponding to odds of about 1 in a few million that the result is a fluke. Babar's detection came in at 14 sigma. The odds of it being a statistical accident were smaller than 1 in a trillion. This was real. Time reversal violation existed, directly seen, beyond any reasonable doubt, built from 468 million particle pairs. To appreciate how hard direct really is here, it helps to see what Babar had to arrange. The experiment produced its B-mesons in entangled pairs, 2 particles born together and quantum linked, so that measuring one told you something instantaneous about the other. By carefully choosing when and how they observed each partner, the physicists could isolate a specific transition, a B-meson turning from one kind of quantum state into another, and then, crucially, isolate the exact reverse transition, the same change run the other way. They compared 4 such pairs of forward and backward transitions, and in every case the rates came apart. This was not an inference from CP violation plus a theorem. It was the asymmetry itself, watched directly, one transition against its own reverse. Nearly half a century separated Cronin and Fitch's original discovery of CP violation from this moment. The 2 men had shared the Nobel Prize in 1980 for opening the door, and only now, in 2012, did someone walk all the way through it and see time's asymmetry face to face. And here is the twist that makes this beat so strange, the reason it deepens the mystery instead of solving it. This genuine law-like arrow of time, the one place where the fundamental laws truly do distinguish forward from backward, is so faint and so confined that it explains absolutely nothing about the time you live in. It shows up only in the decays of exotic particles, in fleeting subatomic events that require billion-dollar machines to produce and study. It has no measurable effect on a cup, on a raindrop, on a human being, on a star. It is a real crack in the symmetry of time, but it is a hairline crack in a foundation the size of a continent, and it cannot bear the weight of the everyday arrow at all. The coffee still cools because of the odds, because of Boltzmann's counting, not because of this whisper in the particles. The two arrows barely speak to each other. There is something almost poignant in this arrangement when you sit with it. The universe does carry a preference for one direction of time woven into its deepest laws, but it hid that preference in the briefest, rarest, most fragile events it knows how to make, and gave it no voice at all in the world where we actually live and grieve and grow old. The arrow you feel every morning, the one that took the people you have lost and will one day take you, is not that fundamental preference. It is the other arrow, the one made of odds, and the fundamental preference, the true one, is a rumour whispered in a language only particle accelerators can hear, saying nothing about your life at all. Two arrows, pointing the same way, that have almost nothing to do with each other. So we are left in a genuinely disorienting position, and it is worth naming it plainly before we go further. The arrow of time we actually experience, memory, aging, the shattering of cups, has no home in the laws. It is a matter of odds, beatable in principle, and, as we have seen, beatable in practice by a machine. And the one true arrow that does live in the laws is so small and so remote that it touches nothing we could ever notice. Time's directionality, the most obvious feature of reality, turns out to be split between a powerful arrow that is not fundamental and a fundamental arrow that is not powerful. Neither one is the thing we assumed we had, and we have not even reached the strangest part yet, because so far we have only been talking about the direction of time. We have not yet touched the order of time, the simple, unshakable idea that causes come before effects. That idea, it turns out, is the next thing the machines take apart, and they do not merely reverse it, they dissolve it. Part 4. When before and after come apart. Everything we have said so far has been about the direction of time, whether it points forward or backward, and whether that pointing is a law or an accident. But there is something even more basic than direction, something so fundamental that we almost never think to question it, and it is this: the idea that events happen in an order, that one thing comes first, and then another thing comes second, that there is a fact of the matter about which of two events preceded the other. You cannot pour the coffee before the cup is under the spout. You cannot read the reply before the letter is written, cause comes before effect. This is the spine of all reasoning, the scaffolding on which every plane and every explanation is built, and it is the next thing the machines take apart. Physicists have a formal name for this everyday certainty. They call it definite causal order, the assumption that for any two events, either the first happened before the second, or the second happened before the first, and that this is simply a fact about the world as solid as anything can be. For the whole history of science, definite causal order was taken as bedrock, too obvious to examine. And then, in the 2010s, a group of theorists noticed something extraordinary lurking in the mathematics of quantum mechanics. They realized that quantum theory, taken seriously, permits something that the everyday world flatly forbids. It permits a superposition of causal orders. It permits a situation in which there is genuinely no fact about which of two events came first, in which the order itself is smeared out, held in a quantum haze, the way a single particle can be smeared across two places at once. To understand how this is even possible, you have to remember the central strangeness of quantum mechanics, the thing that makes the whole subject so hard to picture. A quantum system does not have to be in one definite state. It can be in a superposition, a blend of possibilities that are all, in a real and measurable sense, present at once. A single electron can pass through two slits at the same time. A single atom can be in two energy levels together. This is not a matter of our ignorance, not a case of the electron secretly being in one place while we simply do not know which. Experiment after experiment has shown that the possibilities are all genuinely there, overlapping, interfering with one another like ripples on a pond, until something forces the system to settle on one outcome. Now take that idea, a system being in two states at once, and apply it not to the position of a particle, but to the order in which two operations happen. That is the quantum switch. Here is how it works, stripped down to its bones. Imagine two operations, call them A and B, that you can perform on a quantum system. In the ordinary world, you would do one and then the other, a first, then B, or B first, then A. And the two sequences generally give different results. the way putting on socks then shoes differs from shoes then socks. Now introduce a second quantum system, a control, whose job is to decide the order. If the control is in one state, the machine does A before B. If the control is in the other state, it does B before A. So far, so ordinary. But now put the control into a superposition, both of its states at once, and when you do, the machine enters a condition in which A before B and B before A are both happening, blended together, with no fact of the matter about which order was realized. The two histories overlap and interfere, exactly as the two paths of an electron through two slits overlap and interfere. There is no hidden truth about which operation came first. The order itself has become indefinite. I want to be very clear that this is not a thought experiment, not a mathematical fantasy that lives only on a chalkboard. It has been built in laboratories more than once. The first realization came in 2017, when a team in Vienna led by a physicist named Giulia Rubino constructed a working quantum switch using single particles of light, photons, routed through a carefully arranged optical apparatus. They demonstrated indefinite causal order in the laboratory, an actual physical process in which the order of two operations was genuinely superposed. The following year, in 2018, another group published a sharper demonstration showing that the switch could not be explained away by any hidden, ordinary, definite order secretly lurking underneath. And the results have only grown more rigorous with time. In 2024 alone, one Vienna group performed a complete, exhaustive characterization of a stable quantum switch, mapping out its full behavior. Another team demonstrated the indefiniteness in a single compact device. A year earlier, researchers had even shown that the indefinite order could be certified in a way that requires no trust in the inner workings of the apparatus at all, verified as real using only the assumption that nothing travels faster than light. Sit for a moment with what this means. In these experiments there is a physical process, running on a real device, for which the question, which of these two things happened first, has no answer. Not a hidden answer, not an answer we are too clumsy to measure, no answer, because the order was never definite to begin with. The before and after that structures all of your reasoning, the sequence that lets you say a cause produced an effect, has been dissolved into a fog, and the machine works perfectly well in that fog. It hums along, doing its computation, entirely untroubled by the fact that its own operations have no definite order. The steel spine of causation, the thing you would have said was the most unshakable feature of reality after time's forward march, turns out to be something you can switch off. Now, honesty compels me to tell you that physicists argue about exactly what these experiments mean, and the argument is a real and serious one, not a quibble. Some researchers point out that in every laboratory, quantum switch built so far, there is still a background flow of ordinary time in the room, an ordinary clock on the wall, and the photon is really being routed along different paths within that ordinary time. On this reading, the switch is a genuine superposition of the order of operations, but it may be a controlled simulation of indefinite causation, rather than a true abolition of order at the most fundamental level. Other physicists argue that the distinction is not as clean as it sounds, and that the switch realizes something genuinely new. This debate is unresolved, and a careful person keeps both possibilities in mind. But even the most conservative reading leaves the core fact standing, and the core fact is remarkable enough. Quantum mechanics permits, and machines can realize, a process in which two operations have no definite order, in which the question of what came first has, at the level of the physics, simply been dissolved. There is a reason theorists went looking for indefinite causal order in the first place, and it reaches down toward the deepest unfinished business in all of physics. We have two magnificent theories of the world. One is quantum mechanics, which governs the very small and allows superpositions of everything it touches. The other is general relativity, Einstein's theory, in which time and space are not a fixed backdrop but a flexible fabric, bent and stretched by mass and energy, a fabric that determines, among other things, the order in which events can influence one another. For a century, no one has managed to fully unite these two theories, and one of the places they collide most violently is exactly here, at the order of events. If quantum mechanics allows superpositions, and if the order of events is determined by a space-time fabric that is itself a physical thing, then in a regime where that fabric becomes quantum, near the unimaginably tiny scale where gravity and quantum theory must finally meet, the order of events might itself be placed into superposition. a definite before and after might simply fail to exist. The quantum switch, built on a tabletop out of photons, may be a small, tame shadow of that wild possibility, a preview of what causation looks like when the stage on which events play out stops being fixed. The usefulness of the switch is not hypothetical either. Back in 2015, researchers demonstrated the first concrete advantage, a task that a machine with superposed causal order could accomplish, and that no fixed-order machine could match. Imagine you're handed two operations and asked a simple question about how they relate, whether performing them in one order gives the same result as performing them in the other, or the opposite result. With a definite order, you have no choice but to run them one way, then run them the other way, and compare the two passes, at minimum. But feed them into a quantum switch, with the order in superposition, and the interference between the two overlapping histories can hand you the answer in a single pass. In 2020, another team showed a communication advantage of the same flavor, using indefinite order to send information more efficiently than any ordinary ordered channel allows. The indefiniteness pays for itself. It buys you things that a world with a fixed sequence of events simply cannot provide. What makes this more than a curiosity, and what carries us into the next part of the story, is that the indefiniteness is not useless noise to be cleaned away, it is a resource. A machine that can superpose the order of its operations can do certain things that no ordinary, fixed-order machine can do, can answer certain questions in a single pass that would otherwise require running the operations in both orders and comparing. The lack of a definite before and after is not a defect. It is something you can spend, and once you realize that the order of events can be a controllable resource inside a machine, a resource to be dialed up and used, the last comfortable idea about time begins to wobble. Because if order is a resource, then maybe a single, universe-wide sequence of before and after is not a law of nature at all. Maybe it is just another habit of the everyday world, another arrow made of odds that a machine can put into a fog whenever it likes. Let us follow that thought. Part 5. Order you can spend. Let me try to put you inside the strangeness of indefinite order, because numbers and descriptions can only take you so far, and this is a thing that has to be felt to be understood. So close your eyes, if you're not already drifting, and imagine two events. Imagine a letter and a reply. In the ordinary world, the order is iron. The letter is written first, it travels, it is opened, it is read, and only then, in response to what it said, is the reply composed. The reply depends on the letter, it comes after, the arrow runs one way and cannot run the other. You could never receive an answer to a question you have not yet asked. Now, imagine a machine in which these two acts, the writing of the letter and the writing of the reply, are placed into a single quantum superposition of their order. In one strand of the blend, the letter comes first and shapes the reply. In the other strand, the reply comes first and shapes the letter, and the machine holds both strands at once, overlapping, interfering, with no fact anywhere about which act truly came first. There is no secret sequence hidden beneath. There is no true story that the machine is concealing. The letter and its answer hang together in a chord with no lower note, each one both cause and consequence of the other, and neither one first. Hold that image for a moment, and feel how your mind slides off it, because your mind was built for a world where the letter always comes before the reply. The machine was not. The machine lives easily in a place your intuition cannot go. You might wonder, if this is real, why you have never once encountered it. Why does the ordinary world present such a seamless, unbroken sequence of before and after, if underneath, quantum mechanics allows the order to smear? The answer is the same reason you never see a coffee cup in two places at once, even though the atoms it is made of can be. The delicate quantum blending of possibilities is exquisitely fragile. The moment a quantum system touches its surroundings, the moment a stray air molecule bumps it, a photon of light scatters off it, a bit of warmth leaks in, the superposition is disturbed, and the possibilities that were overlapping are forced apart into a single definite outcome. Physicists call this decoherence, and it happens almost instantly for anything larger than the tiniest, most carefully isolated systems. The everyday world is warm and noisy and endlessly interacting, so the quantum haze of superposed orders collapses into a definite sequence faster than any eye could ever catch. The indefiniteness is not absent from your life. It is simply erased, moment by moment, by the sheer busyness of the ordinary world, the way a whisper is erased in a crowded room. The switch works only because the experimenters go to extraordinary lengths to keep their little system quiet, cold, and alone. That is what indefinite causal order is, and the reason it matters, the reason it is not merely a party trick performed with photons, is the thing we ended the last part on. The indefiniteness is useful. It is a resource. It can be spent to accomplish tasks that a world with a fixed order of events cannot accomplish. And that single fact reframes everything. Think about what it means for something to be a resource. Electricity is a resource. You can store it, spend it, run it down. Fuel is a resource. Information is a resource. These are things you have more or less of, things you deploy to get work done. And now, the order of events, the before and after that you would have sworn was a fixed feature of reality, the same for everyone, everywhere, always, has joined that list. It has become something a machine can hold in reserve and spend, like charge in a battery. You do not spend a law of nature. You do not keep the second law of thermodynamics in a tank and dole it out. But causal order, it turns out, is not that kind of thing. It is the kind of thing you can ration, superpose, and use up, which means it was never quite the law we thought it was. Think, too, about what it costs to spend such a resource, because nothing in quantum mechanics is free. To hold the order of events in superposition, the experimenters have to protect their system from that relentless erasure, and protecting it is enormously expensive in effort and care. This is the same lesson we met with the reversal of the arrow. The strange thing is never forbidden. It is only costly, and the cost is what keeps it out of ordinary life. Nature does not superpose the order of events at the scale of letters and replies, not because it cannot, but because the price, the isolation, the cold, the shielding from every stray disturbance, is one that the warm, crowded, interacting world never pays. And a laboratory is simply a place where human beings agree to pay that price, deliberately, by hand, to see what becomes visible on the other side of the payment. What becomes visible is a piece of the world where before and after are optional. And here we arrive at a pattern that should be starting to feel familiar, because we have now watched it happen twice. We took the arrow of time, the forward direction of everything, and we found that it was not a law but a matter of odds, beatable by a machine willing to pay the price. And now we have taken the order of time, the before and after of cause and effect, and we have found that it too is not the iron law we assumed, but something a machine can dissolve into a fog and even put to work. Two of the most basic features of time, two things that felt like the floor of reality, have turned out to be surfaces with something open underneath. And when the same surprising thing happens twice, in two different ways, a careful person stops treating it as a coincidence and starts asking whether there is a single deeper truth underneath both surprises. Why is time so easy to take apart? Why does every feature of it that we probe turn out to be provisional, statistical, programmable, rather than fundamental? It helps to have a picture for what surface means here, so let me offer one. Imagine you have lived your whole life in a house, and you have always believed the floor beneath you was solid stone, poured all the way down to the centre of the earth. Then one day someone shows you that the floor is a painted canvas, stretched tight and lacquered until it looks and feels like stone, and that beneath it is open space. The canvas is real. You can stand on it. It will hold your weight in ordinary life. You are not wrong to trust it. But it is not what you thought. It is a surface, not a foundation. That is what has happened, twice now, to time. The forward arrow felt like poured stone and turned out to be painted canvas, held up by odds. The order of before and after felt like poured stone and turned out to be painted canvas, held up by a resource a machine can spend. And when the floor turns out to be canvas in two separate places, you stop trusting that it is stone anywhere, and you start to wonder what, exactly, is holding the whole house up. You start to suspect that the answer is nothing you have looked at yet, that the real support is somewhere else entirely, somewhere the everyday eye never goes. There is an answer to that question, and it is the most unsettling thing in this entire story, because it does not come from any new experiment at all. It has been sitting in plain sight, at the very foundation of quantum mechanics, for more than 90 years. The reason time is so easy to take apart, the reason its arrow is only odds, and its order is only a resource, may be startlingly simple. It may be that time was never really in the theory to begin with, that when physicists wrote down the deepest laws we have, the laws that govern everything the machines are built from, they did not put time inside those laws as a real, physical thing. They left it outside. They treated it as a number handed in from somewhere else, a parameter read off a clock on the wall, never a quantity the theory itself contains. And if that is true, if time is not inside the physics but only fed to it from outside, then it is no wonder the machines can bend it. You cannot break what was never load-bearing to begin with. This is not a fringe claim or a wild interpretation. It is a straightforward feature of how quantum mechanics is built, one that every physicist learns and most simply accept and move past without dwelling on the strangeness. In the mathematics of the quantum world, some quantities are real, physical things you can measure: position, momentum, energy, the spin of a particle. Each of these has, in the theory, a precise mathematical object attached to it, the thing you use to predict what a measurement will find. And then there is time, which has no such object at all. Time is the one quantity in the equations that is not something you measure about a system. It is the backdrop against which everything else is measured, and there is a theorem, an old and quiet and largely forgotten theorem, that says this is not an oversight or a matter of convenience. It says time cannot be a measurable quantity in quantum mechanics, that the theory has no room for it, and that the reason cuts to the very heart of what it means for anything to exist and have energy at all. That theorem is where we're going next, and once you understand it, you will never look at the clock the same way again. Part 6. The quantity that was never there. In the year 1933, one of the sharpest minds in the history of physics wrote down a short argument, almost in passing, that should have shaken the foundations of the subject and instead was quietly absorbed and set aside. The physicist was Wolfgang Pauli, a man famous for his ferocious rigour, and what he proved is easy to state and hard to escape. He proved that in quantum mechanics there can be no such thing as a time operator, no mathematical object representing time as a measurable property of a system, as long as energy behaves the way energy actually behaves in the real world. Time, Pauli showed, cannot be a quantity you measure about a system. It has to be an external parameter, a number fed in from outside forever. And the reason is beautiful, and it comes down to a single fact about energy. Let me build the argument up gently, because it is worth following, and it is not as technical as it sounds. In quantum mechanics, there is a profound and famous relationship between certain pairs of quantities, position and momentum being the classic example. These pairs are linked in such a way that you cannot know both perfectly at once. Sharpen your knowledge of one and the other blurs. This is the uncertainty principle, and it flows directly from the mathematical partnership between the two quantities. Now, energy and time look, on the surface, like they ought to be exactly such a pair. There is an uncertainty relation between them that you may have heard of, linking how precisely a system's energy is defined to how long it persists. So it would seem natural that if position pairs with momentum as two measurable quantities, then time should pair with energy the same way. That just as there is a mathematical object for position, there should be one for time, partnered with energy. Pauli showed that this cannot be, and the obstacle is a single, humble fact. Energy has a bottom. Every real physical system has a lowest possible energy, a floor beneath which it cannot go, a state of least energy, the ground state, below which there is nothing. This seems almost too obvious to mention. Of course, energy has a floor. A system cannot have less than its minimum. But Pauli realized that this innocent fact is fatal to any time operator. If time were a genuine measurable quantity, partnered with energy the way position is partnered with momentum, then the mathematics would force energy to have no floor at all, to be able to slide down forever, to negative infinity, without limit. The very partnership that would make time measurable is the partnership that would let energy fall bottomlessly. And since energy manifestly does have a floor, since real systems do have a lower state, the partnership cannot exist. There can be no time operator. Time cannot be a measurable property of a quantum system. It is barred by the simple fact that things have a minimum energy from ever being the kind of quantity you measure. To feel how strange this is, compare time with its near-twin position. Where a particle is located is, in quantum mechanics, a perfectly good measurable quantity. There is a precise mathematical object for it. You can ask the theory where a particle is, and it will give you the odds of finding it here or there, and you can go and check. Position is a property the particle has. But when a particle is somewhere is a different kind of question entirely, and the theory has no object to answer it, because time is not a property the particle has. Time is the thing you consult on the wall while you watch the particle move. This asymmetry runs so far down that it has its own name among the specialists who worry about it. They call it the problem of time, and the problem is not that the answer is hard to compute. The problem is that the question, as the theory is built, does not even make sense. You cannot measure a system's time because its time is not in the system. It is in the clock beside it, and in the clock beside that clock, an external number all the way down, referring always to something outside whatever you happen to be looking at. Stop and let the weight of this settle, because it is the quiet center of the entire story. Quantum mechanics is the most precisely tested theory in the history of science, the theory underneath every other thing we have discussed, the theory the machines themselves run on. And in that theory, time is not a thing that exists within a system to be measured. It is not on the list of real, physical, measurable quantities. Position is on that list. Momentum is on that list. Energy, spin, charge, all on the list. Time is not. Time is the one quantity we treat as the very substance of our lives, the river we are all carried down, and it is precisely the quantity that our deepest theory of reality declined to include among the things that are real and measurable. It sits outside, a number on an external clock handed to the equations from somewhere the equations never specify. This is the floor that was painted on. All your life you have stood on the certainty that time is passing, that it is the most real thing there is, more real than the ground, more real than your own body, because even as everything else changes, time itself flows steadily on beneath it all. And here, at the base of physics, is the discovery. Not a new one, not a headline from last week, but a result that has sat acknowledged and unexamined since 1933, that the theory governing everything never put time among the real things at all. The one fact you are most sure of, the passing of time, is the single fact the deepest theory left off its ledger. It is not that physics looked for time and could not find it. It is that physics built its entire account of reality and never needed to give time a place inside because time was only ever the frame around the picture, never the paint. What is perhaps strangest of all is how calmly the profession has lived with this. Pauli's result did not provoke a crisis. It did not send physicists into the streets. It was noted, understood, and folded quietly into the working practice of the field, where for 90 years it has functioned as a small technical fact that everyone knows and almost no one dwells on. Physicists needed the equations to work, and the equations worked beautifully with time as an external parameter, so they used them and moved on, the way you might drive a car every day without ever asking what happens inside the engine. But the fact never stopped being extraordinary just because it stopped being remarked upon. Underneath the daily business of calculation, the deepest theory of matter was quietly saying something momentous about the nature of the thing we live inside, that it is not at bottom one of the real things at all, and the saying of it went on, unheard, decade after decade, like a bell rung in an empty room. And so we are led, almost against our will, to the question that the rest of this journey exists to face. If time is not among the real things, if it is the frame and not the paint, the clock on the wall and not the world the clock hangs in, then the flow you feel right now, the sense of one moment giving way to the next as you listen, cannot be coming from the fundamental laws, because the fundamental laws do not contain it. It has to be coming from somewhere else, somewhere higher up, somewhere in the relationship between you and the rest of the world, rather than in the deepest rules of either. That idea sounds almost mystical when you first hear it, and yet it was made precise, in careful mathematics, more than 40 years ago, by two physicists who dared to take the absence of time seriously. And decades later, other physicists did something that turns the whole abstract puzzle into a thing you can almost hold in your hand. They took the idea into a laboratory, and they watched time appear, out of nothing but connection. And this reframes every strange thing we have seen so far, gathering them into a single, colder understanding. Of course a machine can reverse the arrow of time. The arrow was only odds, and time itself was never in the laws to protect it. Of course a machine can dissolve the order of events into a fog. The order was only a resource, and time itself was never a fundamental quantity to anchor it. The machines can bend time so easily precisely because, at the deepest level, there was never any solid time there to resist them. The thing we are all standing on, the thing we are all made of, the passing moment, was left out of the blueprint. And that raises a question so strange that for 50 years almost no one dared to take it seriously. If time is not in the theory, if the deepest description of reality contains no time at all, Then where does the time we so obviously experience actually come from? Why do we feel it passing if the equations never mention it? Someone, at last, proposed an answer, and to test it, they built a universe out of 2 particles of light. Part 7. Let us put the pieces together. We have come a long way into the dark, and this is a good place to stop and light a lamp and look at what we are carrying before we go deeper still. Let me gather the 3 findings we have collected and lay them side by side, because separately they are strange and together they are something more than strange. They are a pattern, and the pattern is the real story. The first thing we found is that the arrow of time can be reversed. In a cold machine on a laboratory bench, a small quantum system was made to run backward, its disorder gathering itself back into order, the forward march of time undone by a program. And we learned that this was possible because the arrow of time is not a law at all, but a matter of odds, a habit the universe keeps with overwhelming reliability at large scales, but a habit that can be beaten in a small enough system by anyone willing to pay the astronomical price by hand. The forward direction of everything, it turned out, is not written into the fundamental laws. Those laws run just as happily backward as forward. The arrow was painted on. The second thing we found is that the order of time can be dissolved. Using what physicists call a quantum switch, the simple before and after of cause and effect, the certainty that one event precedes another, that the letter comes before the reply, was placed into a quantum superposition, smeared into a fog in which there is genuinely no fact about which of 2 events came first. And we learned that this indefinite order is not useless noise but a resource, something a machine can hold and spend to do work that no ordinary ordered machine can do. The order of events, like the arrow, turned out not to be the iron law we assumed. It too was painted on. And the third thing we found is the deepest, and it explains the first 2. We found that time is not, in our best theory of reality, a real measurable quantity at all. Position is real. You can measure where a thing is. Energy is real. You can measure how much a thing has. But time is not on that list. A theorem proved more than 90 years ago showed that it cannot be, that the simple fact of energy having a lowest possible value forbids time from ever being a property a system carries. Time is only ever the frame around the picture, a number read off an external clock, never the paint within. And this is why the machines can bend it so easily. There was never any solid, fundamental time inside the laws to resist them. Now set these 3 beside one another and feel the shape they make. The arrow of time, not fundamental. The order of time, not fundamental. Time itself, as a measurable thing, not even in the theory. 3 separate probes, aimed at 3 different features of time, and every one of them came back with the same answer. This is not bedrock. This is surface. This is something the fundamental laws do not contain. When one careful measurement surprises you, you check your instrument. When 2 surprise you in different ways, you begin to wonder. But when 3 independent investigations, using entirely different methods, all point in exactly the same direction, a scientist stops calling it a surprise and starts calling it a discovery. And the discovery here is as large as any in the history of thought. It is that time, the medium of our whole existence, the thing we are so certain of that we build our lives and our griefs and our hopes upon it, may simply not be a fundamental feature of the universe. That word, fundamental, deserves a moment, because everything turns on it. To say something is fundamental is to say it is part of the bottom layer of reality, one of the basic ingredients from which everything else is built, not itself explained by anything deeper. Atoms turned out not to be fundamental. They are made of smaller things. Heat turned out not to be fundamental. It is just the jostling motion of particles. Solidity turned out not to be fundamental. It is the way certain fields push back against one another. Again and again, the history of physics has been the history of taking something that seemed like a basic feature of the world and discovering that it is really the large-scale appearance of something deeper and stranger underneath. And now the same demotion may be happening to time, the most intimate feature of all, the one we would have staked everything on being real, all the way down. There is a comfort hidden in this pattern, if you look for it, and it is worth pausing on before we descend again. Every one of those earlier demotions, atoms into smaller pieces, heat into motion, solidity into fields, felt, at the time, like a loss. It felt as though something solid and trustworthy was being taken away, dissolved into abstraction, and yet each one turned out to be a door, not a wall. Understanding that heat was motion did not make anyone colder. It gave us engines, refrigeration, the whole modern world. Understanding that solidity was fields did not make the ground less able to hold us. It gave us electronics, computers, the very machines this story is about. The demotion of a thing from fundamental to emergent has never once meant that the thing was fake. It has meant every time that we had found the deeper layer underneath it, and that the deeper layer was richer than the surface we thought we understood. So if time is now being demoted in its turn, the honest expectation is not that time will vanish, but that we are about to meet whatever time is really made of. And what it may be made of is the most surprising ingredient of all. But a demotion is not a disappearance, and here we have to be careful and honest. To say time is not fundamental is not to say time is nothing, any more than saying heat is not fundamental means your coffee is not warm. The warmth is perfectly real. It is just that its reality is built out of something more basic. So if time is not fundamental, the pressing question becomes, what is it built out of? What is the deeper thing underneath, whose large-scale appearance we experience as the flow of time? If time is the warmth, what is the motion? Something must be there beneath the surface, holding up the painted floor. And the most daring answer anyone has offered, an answer that sat as pure speculation for 30 years until an experiment made it real, is that time is built out of connection, that it emerges from the way the pieces of the universe are entangled with one another, that the flow you feel is not the universe moving, but the universe relating. To understand that answer, we have to meet the strangest equation in all of physics, an equation for the entire universe in which time does not appear at all. Part 8. Evolution without evolution. There is an equation that physicists have written down for the quantum state of the whole universe. It is one of the boldest things science has ever attempted, to capture everything that exists, the entire cosmos, in a single mathematical statement. It emerged from the effort to combine quantum mechanics with Einstein's theory of gravity, and it is associated with the names of two physicists, John Wheeler and Bryce DeWitt, who wrestled it into being in the 1960s. And this equation, the equation for everything, has a feature so bizarre that when DeWitt first fully grasped it, he found it deeply troubling and referred to it in exasperation as that damned equation. The feature is this: the equation contains no time. There is no clock in it. Nothing in it changes. It describes the entire universe as a single, unchanging, timeless whole. Let that land, because it sounds like a mistake and it is not. When you write down the quantum equation for a single particle, time is right there in it, governing how the particle's state evolves from one moment to the next. But when you scale all the way up and write the equation for the whole universe, the time term drops out. It vanishes. The mathematics of the cosmos as a totality describes something static, a universe that does not evolve, does not tick, does not pass from one moment to the next, because there is no external clock left for it to be measured against. And this makes a terrible kind of sense once you remember Pauli's lesson. Time in quantum mechanics is always an external parameter, a number read off a clock outside the system you are studying. But when your system is the entire universe, there is no outside. There is no external clock, because there is nothing external at all. And so, with nothing to tick against, the universe as a whole simply is. It does not happen. It exists complete and timeless, all at once. It is worth pausing to understand why the time term disappears, because it is not an arbitrary quirk of the mathematics. Think back to what we learned from Pauli. In quantum mechanics, time is always the reading of a clock that sits outside the system under study. You describe how an atom changes by referring to a clock on the laboratory bench, a clock that is not part of the atom. This works perfectly as long as there is always something outside to hold the clock, but the universe is, by definition, everything. There is nothing outside it. There is no laboratory bench beyond the cosmos on which to set an external clock, no room beyond all rooms from which to time the whole. And so, when physicists write the equation for the totality, the external clock that time always depended on has nowhere left to stand, and the time term simply falls away. The timelessness of the universe's equation is not a bug. It is the direct, inevitable consequence of there being no outside, of the universe being all there is. This is called the problem of time in quantum gravity, and it is not a minor technical wrinkle. It is one of the great unsolved puzzles at the frontier of physics. because whatever the equation says, you and I are manifestly not living in a frozen static universe. Time obviously passes. You feel it passing this very moment. Things change. You grow older. The coffee cools. The letter is written and then answered. How can the deepest equation of the cosmos say nothing ever changes, when change is the most obvious fact of our experience? For a long time this looked like a flat contradiction, a place where the theory simply broke. And then, in 1983, two physicists named Don Page and William Wouters proposed a resolution so elegant and so strange that it took the physics community decades to fully absorb it. They titled their idea, with a kind of quiet audacity, Evolution without Evolution. Here is what they saw. Imagine the whole universe really is in a single, static, timeless quantum state, exactly as the equation says. Nothing changing, nothing flowing, the entire cosmos frozen in one unchanging whole. Now imagine dividing that universe conceptually into two parts. Call one part the clock. It could be anything that changes in a regular way, a swinging pendulum, a vibrating atom, the hand of a watch, and call the other part the rest of the universe, everything that is not the clock. The crucial move is this. Let the clock and the rest of the universe be entangled, quantum-linked, their states bound together so that the condition of one is correlated with the condition of the other. Now ask what an observer who lives inside the rest of the universe and who is correlated with that clock would perceive. Page and Wouters showed, in precise mathematics, that such an internal observer would see the rest of the universe changing as the clock's reading changes. They would experience time passing. They would see evolution, even though the universe as a whole is completely static and nothing, globally, is changing at all. This is one of the most beautiful and disorienting ideas in all of physics, so let me say it again in plainer words, because it is the hinge of the whole story. The universe as a whole does not change. It is a single timeless state. But inside it, the pieces are entangled with one another, and time, the time you feel, the flow of one moment into the next, is not the universe moving. It is the relationship between the parts. It is what the correlation between a clock and its surroundings looks like from the inside. An observer who is part of the picture, entangled with the rest of it, reads that entanglement as the passage of time. But an observer who could somehow stand outside the whole thing and take it in all at once would see no passage at all. Only a single, static, eternal state, complete and unchanging, with all its moments already there. Time, in this picture, is not something the universe does. It is something the universe is, seen from within. If the idea of an internal observer seeing time where an external one sees none feels impossible to picture, here is an image that may help. Imagine a film, an old-fashioned reel of film, the kind made of a long strip of frames. Held in your hands, the whole reel is a single static object. Every frame already exists all at once. Nothing on the reel is moving. The beginning and the middle and the end are all equally present, coiled together in your palm. That is the universe as the equation describes it. Every moment already there, the whole of time laid out at once, static and complete. But now imagine a character who lives inside the film, woven into its frames. That character cannot see the whole reel at once. The character experiences the frames one at a time, in sequence, and to them the story unfolds, things happen, time flows. The very same reel that is static and whole from the outside is a flowing story from the inside. Page and Wouters are saying that we are the characters, that the reel is the universe, and that the flow of time we feel is precisely what it is like to be a part of a static whole rather than a viewer of it, to be entangled with the story instead of holding it in your hand. You can feel, I hope, how this gathers up everything we have found and gives it a home. Of course the arrow of time is not fundamental. The fundamental description has no time in it at all. Of course the order of events can be dissolved. Order is a feature of how the pieces relate, not a law stamped on a cosmic clock, because there is no cosmic clock. Of course, time is not a measurable quantity within any system. It was never inside the systems. It lives in the relationships between them. The Page-Wouters picture says that time is emergent, relational, woven out of entanglement, real for those inside the weave and absent for the whole. And if that is right, then the passing of your life is not you being carried down a river that flows independently of you. It is something more intimate and more strange. It is you, entangled with the world, reading your own connection to everything around you as flow. A word about that ingredient, entanglement, because it is the quiet hero of this whole picture, and it deserves to be understood rather than waved at. Entanglement is the profound quantum linking of two systems, a connection so intimate that the two can no longer be fully described on their own. They have properties that belong only to the pair, correlations woven between them that exist nowhere in either one alone. Einstein was so disturbed by it that he called it spooky. It has since been demonstrated in thousands of experiments and is the basis of quantum computing itself. And what Page and Wouters realized is that this same linking, this same weaving together of quantum systems, is what gives rise to the experience of time. A clock entangled with the world it measures is not just recording time from the sidelines. The entanglement between them is what time is. Take away the connection and the flow disappears. Time, on this reading, is the felt inside of entanglement, the way it feels, from within, to be woven into everything around you. For 30 years this was a beautiful idea with no way to test it, the kind of thing physicists debated over coffee and could never pin down. It seemed almost designed to be untestable. How could you ever check a claim about the whole universe being static, from your position hopelessly inside it? And then someone found a way. Someone realized you did not need the whole universe. You needed only a very small universe, a toy universe, one you could build on a laboratory table out of a couple of particles of light. And inside it, if Page and Wouters were right, time itself should appear from the inside and vanish from the outside. In 2014, in a laboratory in Turin, they built exactly that, and it worked. Part 9. A universe made of two particles. The idea that time is built out of entanglement is beautiful, but beauty is not proof, and for 30 years the Page-Wouters proposal floated in exactly that uncertain space, too elegant to dismiss, too abstract to test. How could anyone possibly check a claim about the entire universe being timeless from the inside? You cannot step outside the cosmos and look. You cannot find the external clock the theory says does not exist. The whole idea seemed to live permanently beyond the reach of experiment, a thought too large to ever be caught. And then a group of physicists in Italy had an insight that changed everything, and the insight was this. You do not need the whole universe. You need only a universe small enough that you, the experimenter, can stand outside it. Let me take you into that laboratory, because it is one of the strangest and most quietly profound experiments ever performed, and I want you to see it happen rather than simply be told about it. You're standing in a room in Turin in the year 2014 at an institute devoted to the science of measurement. In front of you is a long, heavy table, its surface pierced with a grid of holes, mounted on legs that absorb every tremor from the building and the street, so that nothing disturbs what happens on top. And what is on top is not much to look at. A scattering of small mirrors and crystals and lenses, and a thin thread of laser light picking its way among them. But something extraordinary is being built on that table. The physicists are making a universe, not a metaphor for a universe, a genuine if tiny closed quantum world made of just two particles of light, two photons, born together in a single event and quantum entangled with each other. One of these photons they designate as the clock, the other is the rest of the universe. And these two particles, entangled, are the entire cosmos of the experiment, a whole world small enough to hold in a single glance. Now watch what happens, because here the abstraction becomes real. There are two ways to look at this little two-particle universe, and they give two completely different answers, and both are correct. First, look at it from the outside, the way Page and Wouters said an external observer would see the whole cosmos. You measure the global properties of the entangled pair as a single joint object, taking in both photons together without asking about one relative to the other. And when you do this, you find that nothing is happening. The little universe is static. It does not evolve. It sits there, frozen, a single unchanging state, exactly as the timeless equation of the whole cosmos predicts. From the outside, there is no time in this universe at all. Nothing moves, nothing flows, but now look at it from the inside. Become an internal observer. Measure the clock photon, read what state it is in, and then, correlated with that reading, look at the other photon, the rest of the universe. And now, everything changes. Now, as the clock photon reads one value and then another, you see the second photon evolving, shifting from one state to the next, changing in step with the clock. From the inside, correlated with the clock, you see time passing. You see the little universe living and moving and unfolding. The very same pair of photons that was frozen and static when viewed from the outside is dynamic, flowing, full of time when viewed from within. One universe, two particles, static from without, flowing from within. And the only difference between the two views is whether you stand outside the entanglement or inside it. How did they actually read the clock, you might wonder, in a universe made of light? The clock they used was a property of the clock photon called its polarization, the direction in which its light wave oscillates, a property that can be rotated smoothly, like the sweep of a hand around a dial. By projecting the clock photon onto one polarization direction, and then another, the experimenters were in effect reading the clock at 1 hour and then at another, and for each reading they reconstructed the corresponding state of the partner photon. Reading after reading, the partner's state marched through a sequence, tracing out a smooth history of change, a little motion picture assembled frame by frame from the correlations between the two photons, and crucially, they could also choose not to read the clock at all, and instead measure the pair as a whole, and whenever they did that, the motion picture vanished and the frozen still life returned. The flow was there only when they looked from inside through the clock. It disappeared the instant they stepped outside and took in the whole. Time was not sitting in the photons waiting to be found. It was created, quite literally, by the act of an internal observer correlating with a clock. This is the Page-Wooter's mechanism, lifted out of pure theory and made to happen on a table you could reach out and touch. Time emerged from entanglement, right there in the laboratory, exactly as predicted. For the internal observer, woven into the correlation, time was real and passing. For the external observer, holding the whole thing at arm's length, time did not exist. The experiment did not prove that our universe works this way. It was a demonstration, an illustration, a small working model rather than a measurement of the cosmos itself. But it showed that the idea is not empty, not mere words. It showed that a static, timeless whole really can contain, within itself, observers for whom time genuinely flows, and it forces upon you a question you cannot easily set down once you have picked it up. Which observer are you? It is a small experiment to carry such a large meaning, and the physicists who did it were careful to say so. 2 photons are not a universe, a laboratory table is not the cosmos, an illustration is not a proof that reality itself is built this way. But the modesty of the demonstration is part of its power. It took an idea that had seemed permanently untestable, permanently trapped among the things you could only argue about, and it found the one clever move that let a piece of it be seen with human eyes. And what was seen was precisely the thing that should have been impossible. A whole that does not change, containing a part for whom everything changes. Once you have watched that happen on a table, even in miniature, you cannot unsee the possibility that you are standing inside the same arrangement, at cosmic scale, right now. Because you, right now, listening to this, feel time passing. You feel this moment giving way to the next. And the Page-Wooter's picture, backed by that little universe in Turin, suggests a reason why. It suggests you feel time passing because you are an internal observer, because you are entangled with the world around you, woven into it, correlated with 100 trillion tiny clocks that are the atoms and molecules of your body and your surroundings. The flow you feel may not be the universe moving past you. It may be the felt inside of your own entanglement with everything, the sensation of being a part of the weave rather than a viewer of it. And if some observer could somehow stand outside the whole of reality the way you just stood outside those 2 photons, they would see no flow at all. Only a single, complete static state. Every moment of your life already there. The beginning and the middle and the end all present at once, coiled together like the frames of a film held in a hand. There is a vertigo in applying this to yourself that is hard to shake once you have felt it. So let me draw it out slowly. You have always assumed that you sit inside a flowing river of time, that the river would keep flowing whether or not you were there to feel it, that time is the great external fact and you are merely a swimmer carried along in it. But if the Turin experiment is a true miniature of how the cosmos works, then the river is not external at all. There is no flowing river that would keep flowing without you. There is only a timeless whole, and your entanglement with it, and the flow is what that entanglement feels like from the inside. Loosen the entanglement, become truly isolated, correlated with nothing, and there would be no flow to feel, because there would be no clock you were reading, no relationship generating the sense of passage. The steadiness of time, its relentless forward motion that seems so utterly independent of you, may be the most personal thing about you, a measure of exactly how thoroughly you are bound up with the world you're made of and surrounded by. You do not move through time, you are woven into it, and the weaving is the moving. I want to sit with you in that thought for a moment, gently, because it is a strange place to rest, and yet there is something in it that is not only frightening. If every moment of your life already exists in that timeless whole, then nothing that has ever mattered is truly gone. The moments you have lost, the people you have loved, the mornings you thought had vanished forever into the past, in the view from outside they are not erased. They are still there, exactly where they always were, fixed points in a landscape that does not fade. It is only from the inside, only for us the internal observers, that they seem to slip away behind us. From the outside, the whole of your life simply is, always, complete. Whether that is a comfort or a terror is perhaps a matter of which observer you choose to imagine yourself to be. And that same double vision, static from without, flowing from within, is not confined to a physicist's table in Turin. It may be the truth about the clocks that run your entire life, the clocks we are about to meet, which turn out to be built particle by particle out of exactly this kind of quantum connection. Part 10. The Clocks We Live By. It would be easy to think that a universe made of two photons is a curiosity, a philosopher's toy with no bearing on the world you actually live in. But I want to close that gap, because the strangest part of this whole story is how ordinary it has quietly become. The idea that time is not found but built, constructed out of quantum systems and their correlations particle by particle, is not confined to a single experiment in Turin. It is, right now, the working principle behind the most precise instruments human beings have ever made. The clocks that define time for the entire civilization are increasingly quantum machines that build time out of exactly the kind of connection Page and Wouters described. Consider what a modern atomic clock actually is. It does not have hands or gears. It works by watching the vibrations of atoms, which tick back and forth between energy states at a rate so stable and so fast that it makes the swing of any pendulum look hopelessly crude. The best of these clocks, the optical atomic clocks, are now accurate to about 1 part in 10 to the 18th. Let me try to make that number mean something, because a bare figure like that slides right off the mind. A clock accurate to 1 part in 10 to the 18th would, if it had been started at the birth of the universe, nearly 14 billion years ago, be off by less than a single second today. It would have kept the entire history of the cosmos from the first light to this moment and lost or gained less time than it takes you to draw one breath. That is not a clock in any ordinary sense. It is very nearly a perfect measurement of the flow of time itself. It is worth understanding just how these clocks reach such precision, because the method is a marvel in itself. Every atom of a given kind is perfectly identical to every other, and each has natural frequencies at which it absorbs and emits light. Frequencies fixed by the unchanging laws of quantum mechanics, the same in every laboratory, on every continent, on every world. An atomic clock tunes a laser until it exactly matches one of these natural frequencies, and then counts the oscillations of that light, which happen hundreds of trillions of times every second. Because the atomic frequency never drifts, never wears out, never depends on temperature or wear the way a mechanical clock does, it provides a standard of time far steadier than anything in the mechanical world. The second itself, the official unit of time for the entire planet, is now defined this way, not by the rotation of the Earth or the swing of a pendulum, but by counting the oscillations of a particular atom. Time, for our whole civilization, is already something we read off the quantum world, atom by atom. These clocks are so precise that they have become instruments for detecting the strangeness of time directly. Einstein's relativity predicts that time runs slightly slower, the lower you are in a gravitational field, that a clock on the floor ticks marginally more slowly than a clock on a shelf, because it sits deeper in the Earth's gravity. For most of history, this was far too small an effect to notice, but the best optical clocks are now so sharp that they can detect the difference in the flow of time across a height of about 1 centimetre, the width of a finger. Lift one of these clocks the height of a coin, and it ticks measurably faster than its twin below. Time is not the same everywhere. It flows at different rates in different places, and we now have clocks fine enough to watch it happen across the space of a fingertip, The steady universal time you imagine is already gone at this level of precision, replaced by a shimmering position-dependent thing that our quantum instruments can map. And here is where the story folds back on itself in a way that should raise the hair on your arms. To push these clocks to their extraordinary precision, physicists have begun using entanglement, linking the atoms together into shared quantum states so that they measure time better as a team than any of them could alone. The very same quantum connection that Page and Wouters said gives rise to time is now the tool physicists use to measure time more precisely. And in one particularly remarkable development, a group at the Massachusetts Institute of Technology reported a new method that they describe, in plain terms, as a time reversal technique. To sharpen their clock, they entangle the atoms, let them evolve, and then run that evolution partway backward, unentangling them in a controlled way, to amplify the faint signal they are trying to read, roughly doubling the precision of the clock. Read that again and let the pieces line up. To build a better clock, a better instrument for measuring the flow of time, they reverse time, in miniature, on the atoms inside it. The reversal of the arrow, which began this whole story as a startling one-off experiment, has become a routine trick of the trade for the people whose job is measuring time. Time reversal is now a tool for making clocks. There is something almost dizzying in that circle. We measure time with machines that build it out of quantum connection, and we sharpen those machines by reversing time inside them. Every layer of the thing we thought was the simplest fact in the world, that time just passes steadily on its own, turns out to be, on closer inspection, something engineered, something constructed, something assembled out of quantum parts by people who have learned to treat time not as a given, but as a material. Even in the most cutting-edge devices, using pairs of trapped ions held in shared quantum states for a fraction of a second at a time, time is not read off some cosmic dial. It is manufactured, particle by particle, from entanglement and control. The clock on your wall and the clock in your phone are the crude, everyday descendants of these machines, and their steady ticking, which feels like a window onto a river flowing past, may be better understood as a construction, a thing we make, not a thing we find. Think about what it means that the second, the humble second, the unit you count under your breath, the beat of your own pulse roughly once a second, is now defined by the trembling of an atom rather than by anything in the sky. For almost all of human history, time came from the heavens, the day from the turning earth, the month from the moon, the year from our long circle around the sun. Time was something the cosmos handed down, immense and external, and we merely kept track of it. But we have quietly stopped taking our time from the heavens and started building it ourselves, in laboratories, out of the most fundamental quantum systems we can find. We took the definition of time away from the rolling planets and gave it to the atoms, and then we entangled the atoms and reversed time inside them to make the definition sharper still. Time is no longer something we receive. It is something we manufacture, and we are getting better at the manufacturing every year. And once you see time as something constructed rather than given, a door opens onto an even older and stranger idea, one that comes not from quantum mechanics at all, but from Einstein, from relativity, from a completely different corner of physics. Because it turns out that quantum mechanics is not the only place where the flow of time, and even the reality of the present moment, quietly dissolves. There is a second road that leads to exactly the same unsettling destination. A road built a century ago out of nothing but the speed of light and the refusal of the universe to agree on what time it is. Two entirely different physics, discovered by different people for different reasons, both arriving at the same demotion of the thing we call now. And when two different roads lead to the same strange place, you begin to suspect the place is real. Part 11. The other road to the same place. Everything we have followed so far has come out of quantum mechanics. The reversal of the arrow, the fog of indefinite order, the absence of time from the theory, the emergence of time from entanglement. But there is another great pillar of modern physics, entirely separate from the quantum world, and it demolishes our ordinary picture of time just as thoroughly by a completely different route. That pillar is Einstein's theory of relativity, and it has been telling us for over 100 years that the present moment, the now that feels so absolute, so universal, so obviously shared by everyone and everything, is not a real feature of the universe at all. Here is the heart of it, stripped of the mathematics. Einstein discovered that there is no universal now. Two events that happen at the same time for you may happen at different times for someone moving relative to you, and there is no fact of the matter about who is right, because both of you are equally correct. Simultaneity, the question of what is happening right now, everywhere, at this instant, turns out to depend on your motion. It is not absolute, it is relative. And this has a consequence so profound that most people who learn relativity are never quite told it plainly. If there is no universal now, then the division of time into past, present, and future cannot be a fundamental feature of reality, because your now and my now can slice through the universe at different angles. An event that lies in your future may already be in my past, and neither of us is mistaken. The only way this can be consistent, the only way both of us can be right, is if all of those events, past and future alike, are equally real. Your future and my past have to both exist, fully and concretely, in order for relativity to hold together. To feel how strange the relativity of now really is, picture something concrete. Suppose you're standing on a sidewalk, and a friend strolls past you at a gentle walking pace. For you, and for your walking friend, the difference in motion is tiny, so your senses of now agree almost perfectly. But relativity says the disagreement, however small, is real, and it grows with distance. Imagine an event happening very far away, say on a planet in a distant galaxy, millions of light years off. Because your friend is walking toward that galaxy and you are standing still, your two definitions of what is happening there right now can differ by days, by years even, depending on the distance. An event that your friend considers to be already in the past, settled and done, you may consider to still lie in the future, not yet happened. And neither of you is wrong. There is no cosmic referee to declare whose now is the true now, because the universe does not have one. The present is not a place the whole universe shares. It is a slice each observer cuts at their own angle, and the slices do not match. This picture has a name. Physicists call it the block universe. The idea is that the whole of space-time, every moment that ever was or will be, exists all at once as a single, unchanging, four-dimensional whole, laid out complete like a landscape. In this picture there is no flowing present sweeping through the block, no moving spotlight of now illuminating one instant after another. Every moment simply is, always, with the same reality as every other. Your birth and your death and this very moment of listening are all equally there, fixed points in the landscape of space-time, and the sense you have of moving through them, of the present sliding forward and the past falling away, is, on this view, something about your consciousness, not something about the universe. Einstein himself came very close to saying this outright. Late in his life, when his lifelong friend Michel Besso died, Einstein wrote a letter of consolation to Besso's family in which he said that people like them, who understood physics, knew that the distinction between past, present, and future is only a stubbornly persistent illusion. He wrote that about a man who had just died. He was saying that Besso had not truly vanished into a vanished past, because in the block universe, the past does not vanish. It is still there. Now stop and feel the shape of what has just happened in this story, because this is the emotional center of the whole thing. We have arrived at the same destination twice, by two roads that could not be more different. Quantum mechanics, working from the very small, from photons and qubits, and the absence of a time operator, tells us that time is not fundamental, that it emerges from entanglement, that the whole may be static while the parts experience flow. And relativity, working from the very large, from the speed of light and the motion of observers, tells us that the present is not fundamental, that past and future are equally real, that the whole of space-time exists at once as an unchanging block. Two theories built by different people from different clues, for different reasons, tested in completely different ways, and both of them quietly remove the specialness of now. Both of them say that the flow of time, the thing you feel more surely than you feel anything, is not written into the universe but into you. This is not one strange idea that you might reasonably shrug off. It is a convergence, and convergence is how physics usually tells you it has found something true. When two independent lines of evidence following different assumptions arrive at the same conclusion, that agreement is far harder to dismiss than either result alone. It is possible that quantum mechanics is wrong about the emergence of time. It is possible that relativity is being overinterpreted when we read the block universe out of it. But it is a great deal harder to believe that both of them, from opposite ends of physics, would independently point at the same illusion, the illusion of a flowing universal now, unless there were something to it. The demotion of time is not the eccentric conclusion of one experiment. It is where the deepest theories we have keep arriving again and again, no matter which door they come in through. Sit for a moment in the strangeness of arriving at the same door twice. Imagine two explorers who set out from opposite sides of a continent, one from the frozen north and one from the burning south, following different rivers, crossing different mountains, guided by different maps, neither one knowing the other exists. And imagine they meet, exhausted, at a single point in the far interior, the same clearing, the same still lake, arrived at from opposite directions. When that happens, you do not think it is a coincidence that they ended up in the same place. You think the place must really be there, must really be where all the paths lead. That is what has happened with time. The quantum physicists, starting from the smallest things that exist, and the relativists, starting from the largest, have walked their separate roads for a century and met in the same clearing, the one where the flowing present turns out not to be a feature of the world. And the fact that they met there, having started so far apart, is the strongest reason of all to believe the clearing is real, and that convergence carries a weight that is not only intellectual. If both of our greatest theories agree that the flowing present is not a feature of the world, then the most immediate fact of your existence, that you are here, now, in this passing moment, and that the moment before is gone and the moment ahead has not yet come, sits strangely unsupported by the physics. It is not that the physics says your experience is false, your experience is as real as experience gets. It is that the physics locates the flow in you, the observer, rather than in the world, and leaves you holding the most vivid thing you know, with no fundamental fact underneath it. That is a lonely place to stand, and an honest one. But before we follow it all the way down to where this story ends, I have to stop and draw a hard line, because there are people who take these true, strange, careful results and stretch them into things that are not true at all, and telling the difference is the most important thing we will do tonight. Part 12. What this is not. Before we come to the end, I owe you a moment of plain honesty, because this is a subject that attracts more nonsense than almost any other, and the wonder we have been building only means something if it is true. Everything I have told you tonight is real, published, careful science. But real science about time gets stretched, in the retelling, into things that are not science at all, and I would be doing you a disservice if I let the strangeness run past the point where the evidence actually stops. So let me draw some hard lines. Not to shrink the mystery is genuine, and it is large, but to make sure that what you carry away from this is the true vertigo, and not a comforting fiction wearing its clothes. When that experiment reversed the arrow of time on a quantum computer, headlines around the world announced that scientists had built a time machine, that physicists had turned back time. They had not. What they did was return a small, isolated quantum system to a state it had occupied a moment earlier by applying a precise and costly operation. Nothing travelled into the past. No person grew younger. No history was rewritten. You could not use this to revisit yesterday, or to undo a mistake, or to send a message to your younger self. The reversal happened to a tiny handful of quantum bits in a controlled machine, and it stayed there. The word time in the phrase reversing time is doing honest work. The evolution of that little system really was run backward. But the leap from that to a time machine is a leap the physics does not support and never claimed to. The experiment is stranger and quieter and more interesting than a time machine. It does not carry you anywhere. It tells you something about what the arrow of time was made of all along. The same caution applies to the fog of indefinite order. When you hear that a machine can dissolve the difference between before and after, it is tempting to conclude that the future can now reach back and cause the past, that effects can precede their causes, that precognition or prophecy have somehow been given a scientific foundation. They have not. The indefiniteness of the quantum switch is real, but it is hemmed in by ironclad rules. There is a foundational principle in physics, tested to exquisite precision, that forbids using any quantum effect to send a usable signal faster than light or backward in time. The quantum switch obeys this principle completely. You cannot use it to learn tomorrow's news, to receive an answer before you ask the question in any way you could act upon, or to send information to the past. The order of two operations can be genuinely indefinite inside the device, and yet no message rides that indefiniteness backward through time. The strangeness is contained. It is real within the machine, and it changes nothing about your inability to know or touch the future. There is a pattern here worth naming, because once you see it, you will spot it everywhere. The original scientific papers behind every one of these results are careful, hedged, full of qualifications and honest admissions of what is not yet known. The physicists who wrote them chose their words with great precision, but precision does not travel well. As a result, moves from the paper to the press release to the news article to the social feed. The qualifications fall away one by one, and the careful claim about a 2-qubit system becomes a headline about turning back time. The scientists are rarely the ones exaggerating. It is the retelling that inflates, each step reaching for a little more drama than the last, until the modest, astonishing truth has been swapped for a sensational falsehood. So when you hear something extraordinary about time and quantum physics, the wise move is to ask what the actual experiment did in its smallest and most literal terms. Almost always the real thing is more limited than the headline, and stranger, and more worth knowing. And then there is the largest temptation of all, the one that reaches past physics into the deepest human hopes and fears. If time is not fundamental, if the block universe is real and every moment exists at once, then surely, the reasoning goes, this proves we live in a simulation, or proves that the future is already fixed and free will is an illusion, or proves that our lost loved one still exists somewhere and death is not real. I have to be careful and honest here, because these ideas touch the tenderest places in us. The truth is that the block universe and the emergence of time are interpretations, serious, respectable, defended by brilliant people, but interpretations, not proven facts. They have equally serious rivals. There are thoughtful physicists who argue that the present is real, and the flow of time is genuine, and the experiments we have discussed do not refute them. Nothing we have covered proves the universe is a simulation. Emergent time neither implies nor supports that idea. Nothing here proves your future is fixed in a way that makes your choices meaningless. And nothing here, whatever comfort it might seem to offer, proves anything at all about what happens to us after we die. To claim otherwise is to take a genuine and open question and dress it up as a settled answer, and that is exactly the thing this channel refuses to do. There is one idea in this territory that deserves a more respectful hearing, even though it too remains unproven, and I mention it in fairness. Some physicists take the time symmetry of the fundamental laws so seriously that they build interpretations of quantum mechanics in which the future genuinely does help determine the present, not in a way you could ever exploit to send a message or foresee an outcome, but in the underlying bookkeeping of how quantum events settle. These are called retrocausal or time-symmetric interpretations, and they are the work of serious people, not cranks. But they are one option among several, unconfirmed, and crucially they still forbid any usable signal to the past. Even the boldest respectable idea in this field stops well short of prophecy or time travel. That is how you can tell the science from the fantasy. The real ideas, however strange, always keep the door to the past firmly shut against anything you could actually use. So here is where the honest line falls. The experiments are real, the arrow of time can be reversed in a machine, the order of events can be made indefinite. Time is not a fundamental quantity in our best theory, and it may emerge from entanglement, and relativity independently says the present is not universal. All of that is true, and all of it is strange enough to keep you up at night without a single embellishment. But time machines, messages to the past, proven simulations, guaranteed afterlives, these are not findings. They are the places where wonder curdles into wishful thinking. The real thing is stranger than the fictions precisely because it is true and because it does not offer you any escape. It does not let you revisit the past or read the future or cheat death. It only tells you quietly and rigorously that the time you're living inside is not what you thought it was, and that, it turns out, is enough. Because when you strip away the false comforts and keep only what the machines have actually shown, what remains is the one question this whole journey has been walking toward, and it is waiting for us now at the end. Part 13. The Song That Exists Only While It Is Sung. So let me finally answer the question we started with, the one I promised you at the very beginning. What are quantum computers revealing about time, and why is it terrifying? Here is the answer, as plainly as I can give it. What these machines are revealing is that time, as you live it, is not a fundamental feature of the universe. Its forward arrow is not a law but a matter of odds, and a machine can pay those odds and run it backward. Its order, the before and after of cause and effect, is not bedrock but a resource, and a machine can dissolve it into a fog. And time itself, as a real measurable thing, is not even present in our deepest theory of reality. It had to be left out, barred by the simple fact that energy has a flaw, and what we feel as it's passing may be nothing more and nothing less than the sensation of being entangled with the world. Every basic feature of time that we have aimed a machine at has come back with the same verdict. This is not the foundation, this is the surface. The floor was painted on, and the terror in that is not the terror of a monster in the dark. It is the terror of vertigo, the feeling of standing on what you were certain was solid ground, and watching it turn to glass, with something enormous and open beneath. Because time is not an abstraction to you. It is the medium of everything you have ever loved and lost. You have lived your whole life inside the certainty that time moves forward, that the past is fixed and gone, that the present is real and the future is coming, that you're being carried down a river toward an end. And now, the machines are quietly telling you that the river may not be a river at all, that the forward flow you feel so surely may be something you are doing rather than something that is happening to you, that the universe, seen from outside, may not be flowing anywhere, that it may simply be, complete and timeless, with every moment of your life already present in it, and the sense of passing may be the felt inside of your own connection to everything, and nothing more. Think back to that cold machine at the very beginning, the one that ran a state backward, that paid by hand the astronomical price the universe never spends. We called it paying the odds by hand, and it seemed at the time like a clever laboratory trick. But hold it now against everything we have learned, and it becomes something else. The universe never pays those odds, and at the scale of your life, neither can you. No machine will reverse the arrow for a human being. No switch will let you visit a moment that has slipped behind you. The reversibility is real, but it lives only in the smallest, coldest, most carefully isolated corners of the world, and your life is not small or cold or isolated. Your life is warm and enormous and entangled with everything, which is exactly why, for you, the arrow only ever points one way. The very entanglement that gives you time is the entanglement that will not let you run it backward. You feel time pass because you are woven into the world, and you cannot unweave yourself to escape it. We first met that phrase, a fact of the matter, in the quantum switch, where the machine had no fact of the matter about which of two events came first. It seemed at the time like a narrow technical oddity about a device on a laboratory table. But watch how far it has travelled. It began as a statement about two operations in a machine, and it has widened, step by step, into a statement about the whole of existence. No fact of the matter about which operation came first became no fact of the matter about which moment is present, which became, perhaps, no fact of the matter about now at all. A phrase that started life describing a photonic experiment has grown until it describes your entire relationship to time. That is how these ideas work. They begin as something small and safely contained in a machine, and then you realize the machine was only showing you, in miniature and up close, a thing that was true about everything all along. Ask yourself then, the question the quantum switch first put to us. Is there really a fact of the matter about now? The machine suggests there may not be. In the switch, there was no fact about which event came first. In the block universe, there is no fact about which moment is truly present. And perhaps, at the deepest level, there is no fact of the matter about now at all. No cosmic present sweeping forward, no universal moment that everything shares. There is only the timeless whole, and you inside it, reading your entanglement with everything as the passage of a present that the universe itself does not single out. The now that feels like the most real thing there is may be the one thing the cosmos has no opinion about. It may be entirely yours. Picture the two pictures as vividly as you can, because the choice between them is, in a way, the whole of what this journey has been for. In the first, feel yourself on the river, the water at your back, the current insistent, the bank sliding past, everything you pass lost the moment it is behind you, the roar of the unseen fall growing slowly louder ahead. It is the picture we are all handed at birth, and it is a picture of helplessness. You did not choose to be placed in the water. You cannot climb out. You cannot slow the current. You can only be carried. Now let that picture go, and hear the second. There is no river. There is only a voice, and a melody rising out of it, note after note, each one sounding into the air and then giving way to the next, not lost exactly, but completed, having been truly sung. The song is not somewhere ahead waiting to be reached, and it is not behind you slipping away. It is here, in the sounding, in the breath moving through it right now, and you are not floating in it. You are singing it. The difference between those two pictures is the difference between being time's victim and being time's author, and the strange gift hidden in everything the machines have shown us is that the physics does not force the first picture on you. It leaves the second one open. And here, at the very end, I want to leave you with the gentlest way I know to hold all of this, because it need not be only frightening. Imagine two pictures of your life. In the first, you are being carried down a river, helplessly, toward a waterfall you cannot see but know is coming. The ordinary picture, time as a current that sweeps you to an end. But there is a second picture, and the physics permits it just as well. Imagine instead that your life is a song. A song does not exist waiting somewhere to be arrived at. It exists only in the singing, note following note. Real in each moment it is sounded, written into no permanent score that the universe keeps on a shelf. And yet the song is not diminished by this. A song is not less beautiful because it is not a stone. It is beautiful precisely because it is happening, because you are the one singing it, because these notes, this moment, this breath, are real in the only way that matters, real in the singing. If time is not a river the universe pours out beneath you, then perhaps it is a song that exists only while it is sung, and you are not its passenger but its singer, and the whole of your life is the music you are making right now, out of your entanglement with everything that is. And if the song is yours to sing, then something shifts in how the losses land too. All through this journey, there has been a quiet grief running underneath. The sense that if time is not real, then everything time has taken is somehow made hollow. But turn it the other way. If the whole of your life already exists in the timeless view, then no moment you have lived is truly annihilated. It is not carried off by a current into nothing. It is there, complete, sung and therefore permanent in the only ledger that could hold it, the fact that it happened at all. The morning you are half remembering as you drift towards sleep, the voice of someone you loved. The ordinary afternoons you assumed were gone. From inside the river they seemed to have vanished behind you. But the river was never the whole truth. From outside they still are, exactly where they always were, notes already sounded in a song that does not unsing itself. You cannot return to them, any more than the machine can reverse the arrow for anything as large and warm as a life. But they were real when they happened, and being real when they happened may turn out to be the most durable kind of existence there is. That is what the machines are revealing about time, and yes, it is terrifying, but it is the terror of standing at the edge of something immense and true, which is not so far from wonder. The cold machine reversed the arrow. The switch dissolved the order. The two photons in Turin held a whole universe, static from without and flowing from within, and all of it points at the same quiet, enormous possibility, that the time you're living inside is not the solid floor of the world, but a song you are singing, note by note, for as long as you are woven into the whole. So rest now, if you are resting. The song is still sounding, and whatever time turns out to be, you are, this moment, exactly where all of it is happening, inside the music, making it, alive in the only now there is.